hopefully talk to some people here in Toronto. So as you're told, what I'm going to talk about today are deep learning of conjugate mappings. Now, this is mostly all coming from a recent paper that I published in Physica D of the same name, so I'll sort of walk you through everything, but most of the results that you're going to see are coming from that paper. Okay, so where I'd like to begin is my all-time favorite subject in all of mathematics, and that is chaos and chaos theory. Now, you know, mathematicians have a habit for naming things with potentially not the best names, but I do think that chaos is probably one of the best names that we came up with in mathematics. And the reason for that is because when we look at the, say, phase space trajectories of a chaotic system, they just seem completely random, completely chaotic. And we know now, after decades of mathematical research, that this is not necessarily the case, right? There is a sort of predictability and a structure to chaotic systems. In particular, we now know that embedded inside of every chaotic attractor, at least for low-dimensional systems, there exists an infinite collection of unstable periodic orbits that densely fill that attractor. You can think of these things as sort of forming the skeleton of a chaotic attractor, and you can really think about, you know, evolving along a chaotic attractor as being close to one of these periodic orbits, but because it's unstable, it's going to thrust you away eventually. And so you jump from the neighborhood of one periodic orbit into the neighborhood of another, spend some time near it, jump into the neighborhood of another one, and so on and so forth with this sort of random jumping fashion.
Do you have to have orbits of all periods?
Sorry?
Do you have to have orbits of all periods?
Not necessarily, no. So the other aspect of this is that this is not just a nice way to think about chaos. It turns out that this is one of the best ways to quantify chaotic systems. So for example, if you have measurable statistics over the attractor, such as something like an invariant measure, or if you're trying to quantify entropy or time averages, you can frame all of these things in terms of the unstable periodic orbits. And so the advantage that this comes with is that if you really want to understand a chaotic system, or even the geometry of the chaotic attractor, then the way that you need to do this is to find and understand these unstable periodic orbits. Okay, so if we're going to begin talking about chaos, probably the best place that we should start is all the way back in the 1890s with the work of Henri Poincaré. So Poincaré is easily my favorite mathematician, just because I really think that he has revolutionized dynamical systems, and he was way ahead of his time. And in particular, in the late 1800s, Poincaré was really interested in understanding solutions to many body problems, in particular the three-body problem. And we all know now, or at least I assume we know, that the three-body problem is a chaotic system. It is very, very hard to quantify the dynamics of solutions to this equation. But at the time, Poincaré didn't really have the tools or some of the mathematical analysis available to him to understand these systems. But he did have a great idea that has sort of stayed with us in mathematics, and that is that he noticed that even though the trajectories of the chaotic system were not periodic, they didn't come back to where they started, they weren't predictable, they were at least recurrent. That means that they could come back to the same region of space that they started in. And so Poincaré's idea was to introduce a lower dimensional transverse to the flow subspace and simply track those solutions every time they hit that subspace. So this leaves you, instead of a continuous time trajectory that flows through space, simply just a discrete collection of iterates asking where you started on that subspace and where you float around to on the next iterate. And so in theory, because we have a collection of points here, there is some theoretical mapping, now referred to as the Poincaré mapping, that iterates you through these successive iterates. Now, Poincaré mappings are typically how we understand chaotic systems. They come with a number of advantages. Now, the first of which is that there is a dimensionality reduction. Now, I know that it's not a huge dimensionality reduction, but technically the phase space is lower dimensional because your phase space is that lower dimensional hyperplane that you're using to collect these iterates in. But the real advantage of using a Poincare mapping is that this is how we understand the sort of geometry and topology of a chaotic attractor. So if you took a chaotic dynamical systems class, maybe you were introduced to something like the Lorentz system that I showed you on the previous board, and then when you start doing the analysis, you jump over to discrete maps and you start talking about chaos in, say, like the Baker's map or the logistics map. And sometimes the correspondence between these things are not clear, but it comes exactly from these Poincare mappings. And the idea here is that you can really understand the topology of these things because those unstable periodic orbits from the previous slide, well, those are exactly the recurrent or the cyclic orbits in these discrete mappings. Now, if there were no disadvantages here, we probably would have solved chaos a long time ago. But the real problem with working with Poincare mappings is that they are nearly impossible to find explicit forms of. Of course, you know, if I give you, say, the Lorentz equations or your other favorite chaotic attractor, if I define a Poincare section, so if I collect all of those iterates in a hyperplane, it's almost impossible to come up with an explicit form for that Poincare mapping that can help you to understand the attractor. And this is really where I want to sort of begin. And I want to emphasize that this is what has preoccupied me for about 2 years now. This is really what I've worked to understand, is how we can find these Poincare maps explicitly, or at least approximately explicitly, and use them to quantify and understand and interpret chaotic dynamical systems explicitly, instead of just talking about in general.
So I guess in this dimension you do have to have periodic orbit small periods, right?
Sorry?
I guess in this dimension where the Poincare section is one-dimensional, then you probably do have to have periodic orbit small periods.
In this case, this is actually a projection of the Rosler. It's just like it's just an illustration to show you that I'm collecting as they go through. So based on what you said on the previous slide too.
Sorry, I was thinking of Sarkovsky's theorem.
Essentially, that's what you have, right? But Sarkovsky's only works for one-dimensional mappings.
So that's why I was saying in this case, the Poincare section is a one-dimensional mapping, yes.
Yeah, exactly. We're actually going to come back to that. Yeah, yeah, exactly. Okay, so before I talk about deep learning, maybe I'll talk about shallow learning. So the sort of naivest possible method to obtain these Poincare mappings in some explicit form. And this is coming from what's known as the SINDY method. So SINDY stands for Sparse Identification of Nonlinear Dynamics. And this is from two of my advisors, Brunton and Coots, and their collaborator, Proctor. So this is from a 2016 paper. And the idea is fantastically simple. So basically what you're going to do is you're going to sample those points in the Poincare section. And you're going to say, if I start at x1, I know that if I flow through space, I come back to x2. And if I start at x2, I flow through space and I come back to x3. And so what you can do is you can organize these things into huge data matrices where capital X1, all of the rows of that data matrix map into all of the rows of capital X2 by this theoretical mapping F, or my Poincare mapping. Now what you can do is, since F is unknown, you can start by doing some sort of simple sort of basis expansion here. I'm going to use a one-dimensional Taylor series just so that you can get the point. But if you wanted to, you could use Legendre polynomials, you could use Fourier expansions, you can mix and match, right? You can use polynomials up to degree 5 and then a bunch of Fourier modes. You can do whatever you want, because the only thing that matters here is tuning these coefficients in such a way that you can best fit your data. And the way that you do this is, you know that if you take a row from capital X1, you feed it into that mapping, you get the corresponding row from capital X2. And so if you do this row by row by row, you're going to set up a massive linear algebra problem where now the unknowns in this linear algebra problem are exactly the coefficients that need to be tuned to fit your data. Now if you do this properly, then you should have an overdetermined linear system. That means that you should have much more data than you have basis polynomials. So you want to collect as much data as humanly possible. For me, it's synthetic data, so we don't have to worry about this. We just simulate the system for a long time. And since this is an overdetermined linear system, there are potentially infinitely many solutions to this thing. So the real question becomes, which one do I want? And if we were going to type this into MATLAB, use a pseudo-inverse or something.
Sorry, if it's overdetermined, you would expect there to be any solution.
Sorry, yeah, you want the best fit. Pardon me, yeah, there's, yes, pardon me. So if you throw this into MATLAB, you can get the least squared solution, but that might not be the best one that you want to look for. And what distinguishes the Cindy method is they tell you which one you should be looking for. And that is the one that uses the fewest basis elements. So that is the solution that is sparse in your coefficients here. And this, the original Cindy method presents this as a sort of Occam's razor type argument. That, you want to use as few as possible because the systems that we see in everyday life, that we create, the Lorentz system, the Rosler system, they're sparse. But I don't really buy that, right? I think that we sort of self-select for the sparse systems that we want to use because they're easy to use. And so really for me, sparsity promotion means a relatively simple mapping that I can work with because the right-hand side is as simple as possible. And so that the way that you find this sparse vector is you will define some threshold parameter. You find the least squared solution here. You comb through those coefficients. Anything that is smaller than the threshold parameter in absolute value gets discarded. That library element is no longer useful to you. And then you repeat this process with your reduced library, and you bootstrap this until you converge to a parsimonious model. Now, what I've been able to show with some of my recent work is that this works really well as long as you don't have chaotic data. So if you are evolving to just a periodic orbit, or if you're some cyclic orbit in your Poincare dynamics, things work well. Quasi-periodicity, that's okay. Chaotic orbits, not so much. And this comes from the fact that chaotic systems are extremely sensitive to parameters. So they're going to be extremely sensitive to this sparsity promotion as well. So this has made me start rethinking how I want to approach discovering these things and how.
Sorry, the lambda is a threshold for how strongly you want to promote sparsity?
Yeah, so it's a hyperparameter, so you can sweep over it and then you can determine what the best fit system is from there. So then, what I've decided to do is approach this from another angle and do a method of indirect discovery. So if you think of what I was doing with this Cindy mapping on the previous slide, that was a direct discovery algorithm. You are directly trying to find that Poincare mapping. But what we can do is we can take advantage of some old ideas from topology, and we can do an indirect method of discovery, for which if we think our original Poincare mapping is mapping from some space X back into itself, we can hope to, at least, find some nonlinear change of variables to bring yourself into a new space Y, and iterate yourself forward in that new space Y, by another mapping G, so that you can transform back to the original space. And so from this commutative diagram, you can see moving from top left to top right is equivalent to moving down, over, and up. Now here's the thing, I can almost hear what everybody is thinking in this room. Why, right? What was the point, Jason? You just told me that it's a huge pain to discover one function. Why would you want to discover two, and one of them has to be invertible? This sounds like it's going to make your life miserable. But the real advantage that this offers to you is that it's through topological conjugacies that we can relate relatively complex systems to relatively simple systems. And let me give you an example. If you've, any sort of dynamical systems or topology textbook that introduces this, typically the following example is on the, right underneath this on the page. You are given some function. In this case, it's the tent map. So in this case, it's a piecewise linear function And we know that there exists this conjugacy function h that will transform f into this simple quadratic polynomial g. Now again, I can hear what you're all thinking. Piecewise linear functions are easier to work with than polynomials. I agree with that from a mathematical perspective, but from a model discovery perspective, the answer is absolutely not. Right? If you think about what I was doing on the previous slide, you are doing this basis expansion in terms of whatever you want to be in your basis. Now, I'm not a particularly creative person. I like using Taylor polynomials over and over and over again. But if you wanted to do this, if you wanted to try and discover the tent map, that means that your basis expansion is going to have to be in terms of some kind of piecewise continuous functions. Where are you going to break up the piecewise, the component where the pieces are put together? In this case, we got lucky. It's halfway in the middle. It's at x equal to 1/2. There's nothing that says that. So the beauty here is that if you can find the conjugacy to transform the variables, model discovery is easy here. You can do it with Taylor polynomials or Taylor expansions. And this is where the deep learning comes in. This is the idea that you want to implement. You want to create a neural network that mimics the idea of topological conjugacy. So if you interpret my entire neural network on the board as just a single function, you take an input, that's your current iterate in the Poincare section, and you push it all the way through, and you get an output, which is your next element of the Poincare section. That is the original Poincare map F. But what you can see from this diagram is that it decomposes the neural network into the individual components that make up your conjugacy. So the first thing that happens is your observable data gets pushed through the conjugacy function to produce the latent variables in the y space. That's h of x. Then you push through the y iterates to see the next time step in y. That's g of h of x. Then once you have the next y iterates, you undo the change of variables to get the next iterate in the observable space, in x space. That's h inverse of g of h of x.
So you're planning to use this neural network to discover both the h and the g, right?
Exactly, exactly.
And somehow you have to constrain it so that the h inverse turns out to be inverse of h.
Yeah, so I left out the details here, but there's a huge loss function essentially that bootstraps all of these individual components. H and h inverse are actually inverses of each other. You know that applying the whole network actually gives you your output that you have. Yeah. So I'm going to sweep all that under the rug for now, but I'd be happy to talk to you about it if you're interested. But so if anybody is familiar with neural networks, this is an autoencoder, essentially. And so the idea here is you're encoding the data into some latent space, and you can decode the data out of that latent space and back. And on the inside, your mapping G is discovered explicitly using a SIND type process. So I can expand it in terms of some sort of expansion, for me, polynomials, for example. And during the training, you're training the encoder, the decoder, and the coefficients on your expansion in G.
Why do you need to train the encoder and decoder separately? Like, is there no way of like adjusting the weights so that there's only one function to train when you're doing the encoder and decoder here?
Yeah, this is all done in one training step. Everything here is trained.
No, sorry. What I meant is that is there no mathematical way to construct a set of related weights on h and h inverse so that you don't need to have the training pass go through all of it?
I'm not sure I quite understand.
It's sort of like shared weights in like a convolutional neural network, where you're here obviously it's different because you have to find the inverse of the function. But is there any way of doing that, or?
I'm not sure I quite understand.
I think what he's saying is, could you train your neural network to just find h and then have an inverse without having to find the inverse separately?
Oh, you want to do those in 2 different steps?
No, he wants to not have to find both of them. He says it should be enough to find one of them and then invert it.
So right now it sounds like you're doing standard propagation, but then putting a really high penalty on h and h inverse not actually being inverses of each other.
Yes, yeah.
And I was wondering if like you had considered trying to like tweak the weights so that they would be that way by design.
Yeah, honestly, I hadn't thought of it that way, but I am intrigued by the idea. Anything that makes performance better, if you think that would improve performance, I'm all for it. This has just not been brought to my attention. Yeah. I don't have much more to say other than that, because I hadn't thought about it. But thank you. But okay, so back to this, some of the strengths that are being offered here, especially as I mentioned autoencoders, one of the things that people think about autoencoders doing is sort of reducing dimensionality, right? You feed in some figure and it maps you to some low dimensional feature space or something like that. You have the same idea that can be employed here. So for example, imagine you take your Poincare section data is 100 dimensional, but it's only representing, say, a 1 or 2 or 3 dimensional attractor inside of that data. Well, what the encoder functions can do here, what the conjugacy can do, is simultaneously project you down onto the manifold that this thing is describing, and then also do a nonlinear change of variable to best fit your reduced mapping. Then the other aspect of this is that you have an improved accuracy for forecasting. And again, this just comes from the fact that you are better fitting your data as opposed to forcing it into this sort of Cindy type discovery process where you have no idea what to expect for your right-hand side. Now, the thing that I like about it is that this gives me a relatively simple mapping, right? This relates complex dynamics to something that is relatively simple. And as someone who actually wants to do a little bit of mathematics on these things, simple mappings are good. They help me out because I can understand relatively complex systems through these relatively simple mappings that get pushed out. And then finally, conjugacies will preserve all of the properties that I am genuinely interested in when it comes to dynamical systems. So for example, things like entropy are preserved over this. And in particular, if you're interested in those unstable periodic orbits, those things will manifest themselves as cyclic orbits in your Poincare mapping. But because the conjugacy preserves trajectories between F and G, that means that you can mine out the cyclic orbits from G and lift them back to the observable space using the decoder here to find the location of unstable periodic orbits in the original Poincare section dynamics of X space. Now briefly, I just want to mention, I did say dimensionality reduction here. There is an obvious question of saying, what dimension should you be reaching for in the latent mappings? And there are a few different ways to interpret this. One of them that we've decided to use is the Lyapunov dimension, or the Kaplan-York dimension. And so one of the signatures of a chaotic system is that it has a positive Lyapunov exponent. So these Lyapunov exponents will characterize the separation of nearby trajectories using just this simple exponential expansion here. And so what you can do by ordering these Lyapunov exponents from biggest to smallest, you can define the Kaplan-York dimension using this kind of complicated looking, kind of ugly formula here. But what Kaplan and York show is that this thing often corresponds to the Hausdorff dimension of a attractor, or of a chaotic attractor. And so you can use this to estimate the dimension of your latent variables. Why? By taking one less than the Kaplan-York dimension. The reason for this is because this is in continuous time. You're reducing yourself down to the Poincare section. And I put an approximate in there because, as you can see from that formula for the Kaplan-York dimension, this thing is rarely going to be an integer, so you're going to have to be doing some approximating here to get yourself into an integer number of dimensions.
Sorry, so the positive Lyapunov exponents are growing, are stretching directions?
Yeah.
And so the Kaplan-York dimension is essentially the number of stretching directions plus this additional term that measures the ratios.
And so I've talked to one of the people who pioneered this periodic orbit theory of chaos, is Predrag Cvitanovich at Georgia Tech. He tells me, he says, just take K. You don't need any of this junk on the end. And that's another equivalent way, or not equivalent, but another way of approaching it.
So the intuition is that the compressed directions all get compressed down.
Exactly.
And it's the stretched out directions that account for how spatially extensive the attractor is.
Exactly, yeah,
Right.
exactly, yeah.
And do you have some easy way of actually estimating the dimension from your data?
Yep, I have like a nice quick quick and easy MATLAB script that'll spit out my Lyapunov exponents, and then you just throw it into this nice little formula. And there are ways of doing it too if it's completely data-driven, you don't have the model. I believe Tim Sauer, my departmental colleague, has some nice ways of estimating Lyapunov exponents from data as well. So if you really wanted to do this, you know.
If you knew the model, then you would be doing this.
Pardon me?
If you knew the model, would you be doing any of this?
Oh, sorry. I mean the continuous time model. I know like the Lorentz systems, but I don't know what the Poincare section is. Okay, so actually, you know, speaking of which, let's take a look at a really simple example. I know that everyone's favorite chaotic system is the Lorentz system. It's not mine. The Rosler system, I feel, does not get enough love in the mathematical community. So I would like to begin the love that this thing should get. So again, much like the Rosler or the Lorentz system, it is a very simple three-dimensional ordinary differential equation. You can see the right-hand side is no more than quadratic, and yet in 3 space we have this extremely complicated chaotic attractor. Now the reason I love the Rosler system is because if you take a Poincare section of x equal to 0, you have a property that on the attractor z is also equal to 0. So it's a provable fact. And so what that means is that you essentially have one-dimensional data that you're collecting in the Poincare section. You're just asking yourself, what is the y value every time you cross x equal to 0? And so what this means is that we can sort of test out the neural network without having to look at the dimensionality reduction aspect of this. One-dimensional data going in, your latent mapping will be one-dimensional on the inside as well. The other thing that I've plotted for you here is the current iterate in the Poincare section yn, and then where it will go to after one trip around the attractor to yn plus 1. Now, everybody is probably looking at that curve and thinking this is a quadratic. Right? This is a quadratic polynomial, or at least approximately. The issue with this is if you look even closer, these lines are just a little too straight to fit a quadratic to it. And in particular, if you do try to fit a quadratic to it, essentially you're just doing the Cindy method. What I've done here is I've applied the Cindy method and I've conjugated the variables in such a way that you can easily compare between the conjugacy model and the Cindy model. Okay? So that means that the only thing that differs between these two models, just for visual representation here, is the leading value on this logistic map that you can conjugate to. Now, you can see that my Cindy model and my conjugacy model, they're both logistic maps. The only difference here is the leading coefficient, 3.6 with Cindy, 3.96 with conjugacy. And you know, it's one thing just to come up with to spit a model out of a computer. It's another thing to determine actually if it's useful, of course. And so the question is, you know, which one of these is a better fit for our data? And so we can go back to our undergraduate chaos class or dynamical systems class. It's a little hard to see. This is supposed to be a period doubling bifurcation diagram. Let everybody use your imagination, interpolate here, right? It's, we know what's happening. But this is the standard period doubling bifurcation diagram of the logistic mapping in terms of the leading coefficient R. So if you get all the way up to 4, you have fully developed chaos, and you're going to period double all the way up to that. Okay, so luckily we can see it on the picture. 3.67, we're somewhere around here. If we go up, we can see that the attractor is composed of 2 disjoint components for this Cindy model. Now, of course, I have eyes, and I can see that my Poincare section dynamic certainly does not have 2 disjoint components. It is one nice connected component. Similarly with the conjugacy model, we are very close to the fully developed chaos region, and you have a completely connected attractor. So immediately, just on the eye test, right, we can see that the conjugacy model is producing, or the conjugacy neural network is producing a much better model. Now, another thing you can do is you can try to forecast the data. And what you can see here in white is the Cindy model for a random initial condition in teal or green, whichever you'd like to call it. you can see the forecasted conjugacy model. And the yellow squares are just simulations, just asking yourself, if you use a Rancho-Cotta scheme or something like that, where are you actually going to go in this Poincare section? Now, what you can see with the conjugacy model, with the Cindy model, is that it falls off almost immediately. And this should not be a surprise, right? That's what we just saw for the bifurcation diagram. It's not describing the same attractor. Whereas the conjugacy model stays on for about seven or so iterates here, reflecting that it's better at forecasting. But, of course, it doesn't stay on for very long, and this is attributed to the fact that this is indeed a chaotic system. Right? It's very, very unpredictable, and you have this sensitive dependence to initial conditions. Now, I know I started this slide by trashing the Lorentz system, but I'm going to come crawling back, and let's talk about the Lorentz system again for a moment. So again, simple dynamical system, quadratic on the right-hand side, and we've seen the butterfly already before. But if you go back and you look at some old dynamical systems work, so such as Guggenheimer and Holmes' very famous textbook on dynamical systems, you'll see an entire section dedicated to what the Poincare section of the Lorentz system should look like. And so what they do is they offer up sort of heuristic arguments, and they say, should be able to conjugate it into a mapping that kind of looks like this, and it should have these kind of properties, I think. And these are the properties that they are able to identify that should be useful in terms of the y1 and y2 here are your sort of latent mapping, your conjugated variables. Now you can see this really nice skew symmetric form. And so what I wanted to do is I wanted to be able to show that maybe Guggenheimer and Holmes were onto something with this. And so what I did is I initiated this Cindy discovery, or a neural network discovery process using the Lorentz systems. I was able to identify a nice conjugacy with this relatively simple skew model. You might be looking at it and thinking that's kind of arbitrary looking, right? You have a sign of y1 in there and you have some absolute values. Essentially what I tried to come up with is the minimal model that fits all of these descriptions here. So it has the discontinuity at y1, it has this odd symmetry property, and so that's why it kind of looks weird. But the idea here was the easiest, simplest model that fits all of those descriptions that is still at least nonlinear. And the coefficients here that are in terms of decimals, those are the ones that are trained on the neural network. So again, it's one thing to just throw a model up on the board and for you to say, okay, looks good, I guess. It's another thing to see if it's actually useful and if it can help us. And so what we can do is we can use this model to extract those unstable periodic orbits that I showed you at the very beginning of this, which were found with this method, for that Lorentz system. So what you can do is you can mine through and find the cyclic points in this mapping. You can use the decoder function to map those things back into the Lorentz system, into the phase space of Lorentz. Now you have points on the Poincare section corresponding to the unstable periodic orbits. You can initialize a shooting method using those as initial conditions. You can set up a root finding problem for periodic orbits with those shooting solutions as your initial conditions. And you can produce basically every unstable periodic orbit. I say basically every because there's infinitely many. So I went for as long as my time span would permit. So I think I got up to about period 20 or something. But the idea here is the symbolic sequences, they represent left going around the left lobe, R right going around the right lobe. You can see that my initial guesses using MATLAB's FSOLVE program is extremely accurate. It's less than 10 steps to get yourself into, I believe it's within 10 to the minus 10 or 10 to the minus 15 error. And the most you're waiting for a solution is about 20 seconds. The other thing is there's been a lot of work done finding these unstable periodic orbits, so you can see if you're actually getting something that has been reproduced in the literature. And one way to reference that is using the period, which is extremely accurate compared to other methods that take much longer to do this. Okay, so what have I really talked about so far? I've talked about two very boring toy chaotic systems, right? The Rosler model and the Lorentz model. Maybe you're not impressed, maybe you don't think it's that interesting, and certainly you shouldn't, right? Because these are low-dimensional, kind of boring chaotic systems, but they work as nice test cases. You know, these are the playground where you can determine if you're actually getting something useful. But of course, what we want to be able to do is we want to talk about much more complicated systems, and in particular, where I would like to move this is into the realm of spatiotemporal chaos. Now, what I've initiated this with is the Kuramoto-Shibashinsky partial differential equation. This has sort of become the prototypical model when it comes to spatiotemporal chaos. You can see it's a dynamical system, so it's flowing in time. The subscripts here are the t is time, x is space. It's fourth order in space. And why this thing has become so interesting, at least for people like myself who are interested in spatiotemporal chaos, is it A, meets the minimal requirement for spatio part of spatiotemporal chaos. It's a one-dimensional spatial medium. It's simple enough. But also, because that nonlinearity is very, very close to the nonlinearity you're seeing in the Navier-Stokes equations. So one of the things that people in this community sort of believe is that if you can get a firm understanding in the Kuramoto-Shibashinsky equation, you might lend itself to understanding spatiotemporal chaos or turbulence in much more complicated realistic fluid models. Now, I'm not going to be so bold to assume that what I'm doing can understand turbulence, but I would like to focus on this equation here. We can see that there's a single parameter, the hyperviscosity parameter nu, and typically the way that people analyze this is using a Fourier or a Galerkin projection. So just following some literature here, you can project onto the odd Fourier modes, and what you get is you get a huge ordinary differential equation in terms of the Fourier coefficients, which are nonlinearly coupled to each other. Now, a relatively recent paper from 2015 decided to look at these systems that result from doing this Galerkin projection, and what they found is, again, actually this is a much better picture than the last one I showed, but this is your period doubling bifurcation, again, into chaos, this time in terms of your hyperviscosity parameter. Now, what I showed you a few slides ago in terms of the Rosler system was that it certainly does not take a high-dimensional system to produce these dynamics. In fact, we can do this with just a one-dimensional mapping such as the Lorentz system. So the goal here would be to see if we can relate this thing, if we can conjugate the Poincare mapping variables into the logistic or quadratic mapping. And in fact, this can be backed up by using the Kaplan-York dimension. You can see that it predicts that the latent variables in this parameter range should be one-dimensional in the Poincare section. And in this case, we use capital N is equal to 14. You can use bigger. It'll be the same, or qualitatively the same. But in this case, then you've got a 13-dimensional Poincare mapping, which along this route of period doubling into chaos, you can relate to the logistic mapping, where you're essentially just tuning what that leading coefficient is. So I give you one example right here. You can see you're at about 3.96. It's very similar to where Rosler was that I showed you. You can see that you are very close to fully developed chaos. And again, it's fun to produce models, but it's not necessarily useful. So what is it that we can actually do with this? We can extract the unstable periodic orbits from this chaotic attractor. So what I'm showing you in the image on the top right is the 10th Fourier mode plotted against the first Fourier mode. In white is the chaotic attractor. Superimposed in blue is just one of the unstable periodic orbits that make up the skeleton of this attractor. Again, really the only thing that sort of limits me is my own attention span. I can pull out tons and tons of these unstable periodic orbits just by mining this simple quadratic mapping for its cyclic orbits, mapping them back to 13-dimensional Poincare section, initializing a shooting method, and using fsolve to find those things. And the nice thing is, so there's one possibility here in that you potentially undercount the unstable periodic orbits, right? The only thing that you are doing is finding a lower bound on them because you're identifying them yourself. Recently, somebody just put a paper on the archive where they coincidentally actually used the same, like almost exactly the same hyperviscosity parameter. And they used manifold learning and some counting arguments to predict what the number of unstable periodic orbits are for this region. And their solution actually comes out to be exactly what I was able to find. So we're finding a nice accuracy and a nice correspondence between these learned conjugacies and these little mappings. How am I doing for time? 5 minutes?
It depends if you want to take questions. So,
Yeah, let's take questions. Yeah.
5 minutes then.
Okay, I will very briefly continue with this, but so it's really the Kuramoto-Shibashinsky equation that I want to keep going with, because this is, as I mentioned, a good frontier for these methods. Right? This is somewhere where you can have actually useful results being produced instead of, say, Rosler or Lorenz, where things are still relatively unknown. And so the other important aspect about the Kuramoto-Shibashinsky equation is that, if you continue to decrease that hyperviscosity parameter, the dimension, as quantified by the Kaplan-York dimension, of the chaotic attractor goes to infinity. It gets very, very, very large. And so you have this sort of testing and proving ground for yourself, where if you just keep decreasing here, things get progressively much more complicated. Now, I'm still trying to follow some of the literature in order to confirm some of these results. So if you decrease a little bit into nu equal to 0.266, you can see that the chaotic attractor here, plotted in the A2 versus A1, so second Fourier component, first Fourier component, it has this sort of, it almost looks like a little crab or something like that. But it is really built of 3 different components. You've got a center and 2 sides. And what you can see on the right-hand side are the spatiotemporal dynamics, where the sort of large period oscillations correspond to being in the center, where these little slurred high-frequency oscillations on the right, correspond to being on the left and the right. And as I mentioned, what you can see, or what you can show here, is that in the middle here, the center component is it's symmetric with respect to flipping the A1 value, and it's a chaotic saddle. So what you eventually find is, after long simulations, you eventually wind up on one of the sides here. And due to the symmetry, those sides are going to be mapped into each other, so they're symmetric, and it's just going to determine what your initial condition will determine where you eventually wind up. Okay, so this is again a region where a lot of people have focused a lot of attention, in particular Cetanovic, who I mentioned earlier. So there's a large body of literature to sort of lean on here to test these methods, but also this is interesting because it's a much more complex scenario than what I just showed in the previous slide. So I'm only going to talk about the center component just for the sake of time here. But Len Cetanovic's analysis of this showed that there is just one expanding direction in terms of the Lyapunov exponent. And so they conjectured that your Poincare map, or your Poincare section dynamics, should be approximately one-dimensional, and it should be ruled by a cubic mapping. So what we can do, just very, very briefly, is discover a nice conjugacy between a cubic mapping here. In this case, you have the symmetry, the y to minus y symmetry. That's coming through from the A1 to minus A1 symmetry from the original attractor. So you're boiling that high dimensional symmetry down into a one-dimensional symmetry. And in this case, you can use some symbolic dynamics to classify all of the periodic orbits that come out of this thing. So you have these 3 regions. You can talk about all of your all of your periodic orbits, just in terms of the symbols 0, 1, and 2. And just to wrap up, what you can do is you can show a complete correspondence with the unstable periodic orbits found by Len and Cetanovic through a very exhaustive method of just sort of guess and check. And in this case, the other thing that the network sort of coincidentally finds is that this thing anchors you around y equal to 0, which turns out to be a sort of organizing center in the chaotic dynamics, or in the chaotic center of the chaotic attractor that happens to be a steady state. So just to see what some of these periodic orbits look like, you can just sort of create a symbolic sequence. You can find the corresponding unstable periodic orbits that go with that sequence. So let me just wrap up so that I don't spill over. You can do the same thing for the side. But the point here is that we've been able to test this with a few different systems now. The Rosler and the Lorentz we talked about, the Kuromoto-Shibashinsky we talked about. We didn't talk about the Mackey-Glass today, but that's a delay differential equation. Again, you can relate it to this nice, simple logistic mapping. Now, as I had mentioned, what I really would like to be able to do is continue with the Kuromoto-Shibashinsky equation. Right? Things get progressively uglier and much more complicated as you start decreasing that value of nu. And so again, I just show you a nice little picture here, further decreased value of nu. And again, using our methods, this is an unstable periodic orbit I've been referring to as the bat, sort of sitting in the middle here. And then where is, oh, sorry. Oh. The last thing that I wanted to say was, where we really want to be able to take this, of course, is to get up to fluid models to extract unstable periodic orbits from turbulent fluid models, and in particular use these things to really understand the state space geometry. And a question that immediately comes to mind from my former advisor at the University of Victoria, who was studying a lot of Rayleigh-Bernard convection, was they have a question when it comes to Rayleigh-Bernard convection of which orbits maximize heat transport, which turns out to be equivalent to asking which orbits maximize these certain long time averages. And there's a lot of conjectures in the relevant literature there where people think that when you're in turbulent regimes, these things are going to be maximized by low period unstable periodic orbits. So of course, if we have a simple way to sort of extract these things out, we can create a nice dictionary of unstable periodic orbits, and we can very, very easily check which ones are maximizing heat transport. Okay, so thank you all for your attention. As I mentioned, this work was conducted, at least initially, while I was working with Nathan Koontz and Steve Brenton at the University of Washington, and then some of the computations were helped out with some undergraduate students who were just exceptional. Thank you.
So you were explaining how to understand what dimensions to expect for this Poincare section. How do you get the actual section? I mean, that's a choice of geometry, right? So in this really high dimensional space, just trying to put the surface in the right place that it catches. How do you do that?
Oh, this is an art in and of itself. Yeah, it's not an easy thing to do. This is part of why I've been using literature to guide me going forward, because people have spent a lot of time thinking about this from system to system. And so if people have already put a lot of time into thinking about this, then I at least have a guidepost. But for the example that I was talking about with this, with the center component here, right? My Poincare section is actually nonlinear. It's a manifold. It's when the second derivative of this is equal to 0, which in terms of the differential equation is this big string of complicated nonlinear equations. It's a very, very difficult task, and so this might this choice of Poincare section makes things look relatively easy. If I use a different one, it might just completely screw things up. And so this is another aspect of this that I do not have an answer to, because it is it's an art, really.
Theoretically, it should only change the conjugating map, right? The important point is just to get to a place where really the system returns over and over again.
Yeah, I agree, right? So if you have, even if you've got something like the Lorentz that sort of just goes in a circle, if you choose some other value for your map, it should be conjugate, because you just flow it forward, right?
So in other words, that would bother you so much, but you somehow have to find a region where you go through often enough.
Yeah, so what happened with this one originally, why I had to use the second derivative, is if you look at the Poincare, or if you look at the solutions here, originally I was using like A1 is equal to 0, and you would miss a lot of the orbits, right? They wouldn't perfectly go through. So for example, this one would only hit once in the center here, whereas it will hit twice up here. And so you have these symbolic correspondences that I was trying to emphasize at the end. You don't see that if you put your section in the wrong place. So yeah, it's an annoyingly complicated task.
Professor Adam Stinchcomb asks, how does the conjugate method perform if the data is noisy? Say, error from the Runge-Kutta solution to the ODEs or measurement error?
Yeah. So I get this question a lot, actually, because I understand, a lot of people are interested in model discovery from like model independence, or if you don't have an exact model. So in terms of noise, it's not really something that I have focused any real attention on, because as I mentioned, really my interest is producing systems that I can do dynamical systems on. So I'm not looking per se at how robust these methods are to noise, because it's just not something that enters a lot of my calculus. But as was mentioned, in terms of simulating with the Runge-Kutta method, that's what I'm doing, right? I'm simulating with the Runge-Kutta method, so that noise is sort of built in when I'm doing this. So I know that, again, maybe it's not a satisfying answer, but it's just not something, it's not an aspect of model discovery that I find myself particularly occupied with at this time.
What happens when you repeat it with a different time stepper?
Well, so what will happen, certainly, so if you imagine you have a time step of 1, say you're really bad at simulating ODEs, right, and a time step of 0.1, you're gonna have some serious noise in terms of the Poincare section, right?
Because I have the time step size. Use 2 different time steppers, like Runge-Kutta 4 versus Runge-Kutta 6, so you're gonna get a different G.
So the only thing that should happen with that is that your gathered data will be off by some imprecision, right? And yeah, so when it comes to training the neural network, everything is numerical, everything is approximate here. So, I don't have a good answer for this, because honestly I don't know. But my guess is it should be relatively similar, because it's still all just a numerical approximation using the network. So small deviations at the 5th decimal place or something like that shouldn't make much of a difference.
With that, let's go ahead and thank our speaker again. And I think our speaker will be around if anyone has any more questions afterwards. And also, we are taking him out to tea.